Understanding word embeddings is a crucial piece of the puzzle in natural language processing, especially within artificial intelligence. These vectors, they really capture the meanings of words in a way that helps machines grasp the context in which those words are used, making them absolutely indispensable for tasks like sentiment analysis, translation, and text classification. Now, up to this point, we've touched on the unique challenges of representing text in AI, emphasizing the abstract nature of language itself. We've also explored some techniques for translating text into numerical embeddings, things like word-to-vec, glove, and those contextualized embeddings from models like BERT, which really underscore the necessity of considering word context. Don't forget, we also talked about the critical role of text pre-processing in optimizing the performance of our NLP models. This includes clever visualizations that help us understand word relationships within embedding spaces. Just think, continuous research and advancements in text representation are going to keep enhancing AI applications across a variety of linguistic tasks. So, let's dive deeper into word embeddings and their applications. We're going to explore how they offer a more distributed representation of word meanings, setting them apart from traditional sparse representations. It's quite fascinating, isn't it? Now, let's dive into how we can implement the word-to-vec model to create word embeddings using the GenSim library in Python. First, we start by importing the necessary modules from GenSim, and don't forget to download the NLTK tokenizer. It's essential for breaking down our text into individual words. After that, we'll define a list of sample sentences that highlight concepts relevant to artificial intelligence and natural language processing. Next up, we proceed to tokenize these sentences. This means we're converting each sentence into lowercase and splitting it into individual words, which results in a structured format that the word-to-vec model can easily process. Now, let's implement the word-to-vec model training by providing the tokenized sentences. The parameters we set for the model, like vector size and window size, really influence how the word embeddings are created, capturing those contextual relationships between words. Once the model is trained, we can explore the resulting word embeddings. By querying the model with specific words, we get to see the vector representations for terms like artificial and language. This allows us to understand just how these words are encoded in high-dimensional space. This practical implementation really exemplifies how word embeddings facilitate a deeper understanding of language in AI applications. The bar chart titled Effectiveness of Different Word Embedding Techniques displays effectiveness ratings on a scale from 0 to 100 for 4 popular methods. Word-to-vec scores 80, Glove sits at 75, BERT leads the pack at 90, and TF-IDF comes in last with a score of 70. Now, let's break down what we see here. First off, BERT's impressive rating of 90 suggests it has a significant advantage, particularly because of its contextualized, transformer-based approach. Meanwhile, the static methods like word-to-vec and glove are surprisingly close, with word-to-vec edging out glove by just 5 points, scoring 80 compared to glove's 75. And then we have TF-IDF, bringing up the rear at 70. This really drives home the limitations of traditional, sparse bag-of-words models when stacked up against the denser embeddings. From these insights, we can draw some practical conclusions about choosing the right model. If you're dealing with tasks where understanding the context is key, BERT-like embeddings are certainly the way to go. On the other hand, if you're short on computational resources or facing latency issues, both word-to-vec and glove are solid alternatives. And while TF-IDF might just cut it for simpler tasks, it generally underperforms when it comes to capturing semantic meaning. Finally, the chart's detailed axis labels and numeric annotations on each bar make it super easy to see the relative performance gaps. So, as you analyze these methods, keep these points in mind for your modeling journey. Now, let's dive into how we can load Glove embeddings using Python, shall we? We've got this handy function called load Glove model, which takes the file path to your Glove text file as an argument. First off, it initializes an empty dictionary to hold the embeddings. As the function reads through the file line by line, it splits each line into the respective word and its vector representation. So this is pretty clever. It takes that first element as the word and then transforms the remaining space-separated strings into a NumPy array of floats. By doing this, we're effectively storing each word alongside its vector in the dictionary, creating a neat little structure that allows for quick access to those embeddings. All right, once we've defined our function, we move on to loading the Glove model by supplying the specific file name for the Glove embeddings. Now, it's super important to make sure that this file is accessible in your working environment. After we load the embeddings into our dictionary, retrieving the embedding for any word, say technology, is as easy as referencing the corresponding key in our dictionary. This method really showcases how Glove beautifully blends both statistical relationships and contextual information to enhance word representation in natural language processing tasks. Now, let's see how we can implement BERT using the Hugging Face Transformers library, which really makes working with pre-trained models for natural language processing tasks a breeze. First up, we start by importing the necessary classes, so that's BERT Tokenizer and BERT Model, and we'll also bring in the Torch library for those tensor manipulations. Now, the next step is to load our pre-trained BERT model along with its tokenizer. We do this using the FromPretrained method, and we're specifically going to specify the model name as BERT-base-uncased. This way, we're tapping into a robust, widely used version of BERT that's perfectly capable of generating those all-important contextualized embeddings. After that, we'll set up our input text, which is basically a sentence where we want to dig into the contextual meaning of the words. We can then proceed to tokenize this input using our tokenizer, converting our sentence into a format that BERT can make sense of, and ensuring it's returned as a tensor. To grab those embeddings, we're going to run the model within a context manager that disables gradient computations for a little boost in efficiency. The model will then output a structure from which we extract the last hidden states, which represent those contextual embeddings for each token in our input sentence. And it's really fascinating how these embeddings dynamically adjust based on context, reflecting how BERT captures those rich semantic relationships in language. Now, let's implement a pre-processing function to ensure our text data is clean and suitable for embedding models. The first step is to import the necessary libraries. This includes R for regular expressions, as well as NLT case tools for handling stop words and lemmatization. So make sure you download the required NLTK data first. After that, we define our function pre-process text. This function starts by converting the input text to lowercase to maintain uniformity. Next, we use a regex operation to remove any punctuation and numbers, which means we're focusing solely on alphabetical characters and spaces. This is super important because it helps eliminate some noise that might mess with our model training. After that, we split the clean text into tokens, which are essentially individual words. Now, to further refine these tokens, we filter out any that are identified as stop words. These are common words like and or the that don't add much meaning. Then, we employ the WordNet lemmatizer to convert words into their base forms, which really helps standardize the linguistic variations we encounter. Finally, we join the tokens back into a single string. This clean text is essential for ensuring higher accuracy when we're feeding data into our embedding model, allowing us to achieve improved performance in later NLP tasks. Now, let's implement the following code to visualize word embeddings using TSNE. First, we need to prepare our words and their corresponding embeddings by extracting them from the Glove model, okay? So, we're going to store the words in a list and convert the embeddings into a NumPy array for efficient processing. This setup is really vital as it organizes our data for the upcoming dimension reduction technique. Next up, we'll apply TSNE, and we'll specify the parameters like n components equals 2 for our two-dimensional visualization. We'll also include a perplexity value and the number of iterations to ensure that we achieve effective convergence. This key step reduces those complex high-dimensional embeddings into a lower dimensional space, which allows us to represent the relationships between words more intuitively. After we get those reduced embeddings, we'll move on to creating a scatter plot using matplotlib. Let's define the figure size for better clarity and plot those reduced embeddings. Each point on the plot will represent a word positioned according to how similar its embedding is to others. Finally, we'll annotate these points with the respective word labels, making it super easy to identify terms and visualize their relationships in this two-dimensional context. This whole process enhances our understanding of the semantic similarities between words in our embedding space, and it's a really exciting step in your data exploration journey. In conclusion, word embeddings are a cornerstone for more advanced applications in natural language processing. Their ability to encapsulate semantic meaning in a distributed manner has truly transformed how machines understand language. From word-to-vec and glove to BERT, each type of embedding offers unique qualities and capabilities that adapt well to various NLP tasks. Continuous research is enhancing these techniques, paving the way for even more intelligent AI systems. Now, as we delve deeper into the world of word embeddings, it's vital to remember they're not merely a technical necessity. They're like a bridge connecting our communication with machines. This bridge provides a richer understanding of human language, which can significantly enhance how we interact with and utilize technology. So, I encourage you to explore, experiment, and really let the power of word embeddings elevate your AI projects to new heights.